Imagine hunting for one friend in a huge hall. If everyone is seated in random order, you have no choice. You start at one end and check every single face until you find them. But if they are seated strictly in increasing order, everything changes. You glance at the middle, compare, and instantly throw away half the hall, then half of what's left. This lesson is those two strategies, linear search and the beautifully fast binary search, and exactly why one is order n and the other order log n. Linear search makes no assumptions at all. Here is an array of 8 numbers, indexed from 0. We want the key 19. The plan is simply walk from the left and compare each box with 19, one at a time. Box 0 is 3, not 19. Move on. Box 1 7, still no. Box 2 11. Keep going. Box 3 15, not yet. And box 4 is 19. A match. We stop and return index 4. It took 5 comparisons to get here. Now the worst case. Suppose the key is 100, not in the array at all. Then we are forced to check every last box before we can be sure it is missing. All 8 comparisons. So for a list of length n, the worst case is n comparisons. And on average about half of n. Both grow straight in line with n. We write that as order n. The one bright spot. If you get lucky and the key sits first, it is a single check. Order 1. Here is the star of the lesson. Binary search. Its one demand is that the array is already sorted, smallest to largest. We will hunt for 23 in these 10 numbers and watch the search space collapse. We keep 2 markers. Low starts at index 0, the far left. High starts at index 9, the far right. The answer, if it exists, is somewhere between them. Step 1. The middle index is low plus high over 20 plus 9 is 9, halved and flawed, gives 4. Look at box 4. It holds 16. Compare. 16 is less than 23. So if 23 is here at all, it must lie to the right of the middle. We throw away the entire left half, boxes 0 through 4, in one stroke. Step 2. And now we only ever look at what survives. Low is 5, high is 9. The new middle is 5 plus 9 over 2, which is 7. Box 7 is 56. This time 56 is bigger than 23. So 23 must sit to the left of here. We discard the right half, boxes 7, 8 and 9, and pull high down to 6. Step 3. Only 2 boxes are left, 5 and 6. Low is 5, high is 6. The middle is 5 plus 6 over 2, flawed, which is 5. Box 5 holds. 23, a perfect match. We return index 5, and it took only 3 comparisons. Linear search would have taken 6 to reach that same box. Look what happened to the search space. 10 boxes, then 5, then 2, then 1. Each step cut in half. Let's count binary search's worst case exactly. Call f of n the most comparisons it can ever need on an array of size. N each step does one comparison, then recurses on a half of size n over 2. So f of n equals f of n over 2 plus 1, and f of 0, an empty window, is 0. Unroll it, and every step just adds 1 until the size hits 0. That gives a clean closed form. F of n is the ceiling of log base 2 of n plus 1. The plus 1 and the base 2 both matter for an exact count. Let's use it on a real number. 8,000 items. Peel the recurrence. F of 1,000 is f of 500 plus 1, which is f of 250 plus 1, and so on, 1,000, 500, 250, and downward. Keep going. 31, 15, 7, 3, 1, and finally 0. Count the plus ones. There are exactly 10 of them. So f of 1,000 is 10. 10 comparisons, worst case, to search 1,000 sorted numbers. Cross-check it against the formula. 2 to the 9th is 512. 2 to the 10th is 1,024. 8,001 sits between them. So the ceiling of its log base 2 is 10. The two methods agree. Always a good sign. Why is halving so powerful? Every comparison deletes half of what remains. So the size of the search space marches down like this. N then, n over 2, then n over 4 over 8, until only one box, or none, is left. The number of halvings needed to shrink n down to 1 is log base 2 of n. That is the whole reason binary search is order log n, while linear search is order n. And that gap is not small. It is astonishing. Put real numbers on it. For 10 items, linear may need up to 10 checks. Binary, at most 4. For 1,000 items, 1,000 checks versus about 10. And for 1,000,000 items, brace yourself. Linear can take a full million comparisons, while binary needs only about 20. 20. That is the difference between instant and hopeless. Let's write it down cleanly as a loop. Low begins at 0, high at n minus 1. Then, while low is less than or equal to high, we keep going. Inside, compute mid with integer division, floor of low plus high over 2. Then 3 branches. If the middle equals the key, return that index, done. If the middle is too small, the key must be to the right. So move low up to mid plus 1. If it is too big, the key is to the left. So move high down to mid minus 1. And if the loop ever ends with low past high, the window is empty. Return minus 1 meaning not found. What happens when the key simply isn't there? Search the same sorted array for 20, which is missing. Middle is 16, too small, go right. Next middle 56, too big, go left. Next middle 23, still too big, go left again. Now high has dropped below low. The window is empty, nothing left to check. So we stop and report not found. In just 3 comparisons. The collapsing window is binary search's way of proving the key was never there. But here is the catch that ruins everything. Binary search only works on sorted data. Watch it fail. This array is not sorted. 19 sits before 15. We search for 15, which really is here. At index 4, middle is index 2, which holds 11. 11 is less than 15, so binary search confidently throws away the left half and looks right. Next middle is 19, bigger than 15, so it throws away the right and looks left. And now the window is empty. It declares 15 not found. Dead wrong. Because 15 was sitting right there the whole time. The go left, go right logic is only trustworthy when the data is in order. This is exactly why sorting matters, and it's where we head next. Your turn. Here's a fresh sorted array of 10 numbers. Pause the video, run binary search for 42 by hand, and count exactly how many comparisons it takes. I'll wait. Here's the walkthrough. Low 0, high 9, middle 4 holds 28, which is less than 42. Go. Right, low becomes 5. That is comparison 1. Middle of 5 and 9 is 7, holding 50. Bigger than 42. Go left. High becomes 6. Comparison 2, middle of 5 and 6 is 5, holding 35. Still less than 42. Go right. Low becomes 6. Comparison 3, now low and high both point at 6. Middle is 6 and box 6 is 42. Found. At index 6 in exactly 4 comparisons. If that's what you got, you have truly understood binary search. Trap 1, the deadly one. Binary search demands sorted input. On unsorted data, its decisions are meaningless and it will miss keys that are present. If the data isn't sorted, either sort it first or just use linear search. Trap 2. Computing mid as low plus high over 2 can overflow in languages with fixed size integers when both are enormous. The safe form is low plus the quantity high minus low over 2, mathematically identical, but it never overflows. Trap 3. Off by 1. After checking mid, you must move past it. Low to mid plus 1 or high to mid minus 1. Forget the plus or minus 1. And the window stops shrinking. And the loop spins forever. And trap 4. The loop condition is low less than or equal to high. Use a plain less than, and when low equals high, a single box left, you skip it entirely and wrongly report not found. Let's lock it in. Linear search scans every element in turn. It's order n, and it works on absolutely any array, sorted or not. Binary search halves the search space with every comparison. Order log n, breathtakingly faster, but only ever on sorted data. And the recipe you should be able to write in your sleep. Middle is floor of low plus high over 2. Move low to mid plus 1 or high to mid minus 1. Loop, while low is at most high. Master those 3 lines, and no search will ever slow you down again.